Okay, so we start B. We get the vertical asymptote by equating x squared minus x minus 12 to 0. Then it becomes a quadratic. Wow, I don't like the issue of factors, so I'll use the formula 1 plus or minus the root of 1 plus 4 by 12, that's 48 over 2, which is 1 plus or minus 7 over 2. There's a question from KB.
Oh yes, sir. I wanted to I wanted some clarification on finding the sample that and using the quadratic equation. Okay, I usually call it the bus. Yeah. Whether you use the sum and product or use the quadratic equation for negative b plus or minus, we still get the same answer.
Not negative b plus or minus. Oh yeah, you get the same answer.
Get the same answer, so it doesn't matter whether you
Sir, I can't get what is being talked about.
The question is, do you get the same answer if you use the general formula or use the product in something?
Yes.
So you're saying we get the same answer.
right thing.
Okay. So here we have like 8 over 2 or negative 6 over 2. So x is equal to 4 or x is equal to negative 3. These are the vertical asymptotes. Now we go for the horizontal asymptote. So we'll get the limit as x goes to infinity. The greatest power down is 2. So we have 1 minus 1 over x minus 12 over x squared. And on top, we take the same x squared. That will mean we'll have 2 over x squared. So you divide it throughout so that this x squared and this one can cancel. And then we remain with the limit as x goes to infinity of 2 over x squared over 1 minus 1 over x minus 12 over x squared. So because this is 0 on top, remember a over x, even if x is squared or to any power, you get 0 over, it does not become over 0. Because this is 0, but we have a 1. So a 1 helps us to have this thing defined. Remember, if you use the shortcut, you just observe that the numerator has the power of x rather than the denominator. Hence, the horizontal asymptote is equal to 0. But I think I observed that in most test scripts that I marked, people are getting confused here. They didn't know what to compare, so they will end up saying the vertical asymptote is that thing, or the horizontal asymptote is that thing. Like you can't really differentiate. So also I'm trying to bring in this other method so that those who had the confusion of how to differentiate, they'll go for this method. Moreover, since we'll be doing calculus very soon, this becomes the best because this is what holds calculus. So let's start with KB.
No, sir, you have already answered my question.
Okay, then we'll go to, how do I pronounce it? Adi. What's your question?
Adio.
Adi, all right.
Sir, I'm confused. Now you are coming up with 2 over x, how you are factorizing that x. I was hoping that I will understand in the next example, but no, doesn't work.
Okay, look, when you're doing if we say this is 2x squared plus 3x minus 4, and then we say, suppose this is a quadratic, then we say, this is a quadratic. Now, suppose we want to use computing the square, we would say factor out 2. Then you do like 2 outside, and then you divide 2x squared divided by 2, you get x squared, plus 3x divided by 2, you get 3 over 2x minus 4 over 2. And we called it factoring out. Now this process is what we are doing here, because we had x squared minus x minus 12. Now we are factoring out x squared. So you factor out x squared. Yeah, you get the recording, don't worry. So you factor out x squared, then you have x squared into x squared, you get 1 minus x over x squared. This will be 1 over x. So we have 1 over x, and then 12 over x squared, which remains 12 over x squared. That is in the denominator. In the numerator, in the first place, there's no x squared. So when you factor out x squared, even if it's not there, then you divide throughout by the same. So you divide 2 over x squared. And that is what we are calling factoring out in this case. That's how the highest powers of x are getting out. I hope it's okay now. And,
Yes, we're heading somewhere.
all right. Let's keep it in there.
So from the same point, how have you come to 0?
Then now, how do we get to 0? Remember, is what we wrote in the previous class. We said the fact, the limit as x goes to infinite of any number over x to any power is equal to 0. This is the fact. That's how we call it in first year, because in first year don't prove everything. We just use some statements as they are. So that is the case. So everywhere where you see a number over x and the limit goes to infinite, it gets to 0. Remember, I'm saying, please get it. I'm saying going to infinite, not any other number, but to infinite, it becomes 0. Okay, then the y-intercept.
So I have a question first.
What is your question?
So is it wrong to just observe the horizontal asymptotes? Yes.
There's nothing wrong in observing. As long as it works well for you, you can observe.
Okay, thank you.
All right. So the y-intercept.
Wouldn't that be suicide?
No, we used remember in test 1, we didn't have limits. So we're just observing. And it worked.
All right, sir.
Okay. Then the y-intercept, we do f of 0. So we get 2 over negative 12. That is 1 over negative 6. Where there is x, we've taken 0, 0. So we have negative 12 in the denominator. On top, there was no x actually. X-intercept. We equate the numerator to 0. And the guy can never be 0. So no x-intercept. Hope you understand that. There's no x in the numerator. So we said equate it to 0 and solve for x. Now there's no x. So you can't force it. It means there's no x-intercept. Then now we sketch. So to sketch, we have two horizontal asymptotes, -3, two vertical asymptotes. We can never have two horizontal. So we have -3 and +4. +4. Then, what is the y-intercept? The y-intercept is -1/6. Yeah, and there's no x-intercept. So this means that the graph in between here will just be a very bad graph of this nature. Normally, we are guessing that the turning point will be on the bigger space. What do I mean by bigger space? We have from -3 to 0. This is like 3 units to the left. Then we have 4, meaning 4 units to the right. So it means that this one becomes the bigger space. So we'll guess that the turning point is in the bigger space. What is the y-intercept? It's like we didn't show the y, there was one asymptote. It is y is equal to 0, which is the x-axis. That's why we have not touched the x-axis. If there was the x-intercept, yeah, we would have crossed the x-axis. But there isn't an intercept there, so we can't even attempt to cross. Now we go to the right of this 4 and pick, let's say 5, and take it in the original function. So we'll have f of 5. Where do I do it from? Let me do it from here. This thing, f of 5, that is going to be 2/25 minus 5 minus 12. That is 2/25 minus 17. So 3 plus 5, 8. So we get 1/4. It is greater than 0. What is 0? The horizontal asymptote. So it means that the curve is going to be up here. We picked a number 5. We picked a number 5 as x, which was greater than 4. What is 4? The vertical asymptote. What is 0? The horizontal asymptote. You pick a number using the vertical asymptote. You compare with the horizontal for you to plot your graph. Mono.
Sir, I'm kind of lost. How did we find the y-intercept? More especially on the -12 part.
Okay,
On
the
the denominator.
y-intercept. So the y-intercept, wherever there is x in this function, you put 0 here, you put 0 here. So you have 0 minus 0 minus 12. So then the whole geometer will just reduce to -12.
Oh, okay.
Okay, now we go to -3. So x is equal to -3. Then we pick a number. So let me start that way. Let's pick x is equal to -4, a number less than -3, the vertical asymptote. Mr. Brandon, the power of x, what do you mean? Oh, so when you put a 0, well, 0 to the power 2 is still 0 minus 0 minus 12. Okay, Linda, I'll come back to that too. So the power of x did not affect the outcome. Okay, good. So we pick -4, which is less than -3, where -3 is the vertical asymptote, and take it in f. What is f of -4? This is 2 over 16 plus 4 minus 12. This is going to be 2 over 16 minus, okay, 4 minus 12, that is -8. 16 minus 8, that is 8. So we get 1 over 4. This number is greater than 0, the horizontal asymptote. So again, the curve is going to be up here. That's how we sketch it. How do we come up with this curve in between here? This curve here. Well, we're supposed to test numbers that are in between -3 and 4. So we tested, annoyingly. We got x is equal to 0. This 0 is in between -3 and +4. It lies in this interval. So we substituted it in the function and got -1 over 6. -1 over 6 is less than 0, the horizontal asymptote. So it means that we are going to have a curve down here. Now this curve, well, it could have been like this. But look, it becomes very hard for it to be like this one, because it's bounded by 2 lines. There's a line on the right, there's a line on the left. So it means that it should be like a quadratic. So we try to force it to look like that. In forcing, it must turn. So we just guess this turning point. The right guess will be something between -4 and, -3 and 4, exactly in the middle. But we can't get there. But at least we know that the half of this will be to the right of 0. And then we just place the intercept here and then have the curve. But calculus will come in and help us very soon on how to get the turning point here, the actual turning point. So when we get it, it will become easy for us to operate. So I wanted us to do some other things, but I think we won't. We'll just do another example. Better slow and we understand.
So it's always you are supposed to come up with 3 pieces, like what we have drawn there on the graphs.
Not always 3 pieces. It depends with the number of asymptotes that you have. If you have 2 asymptotes, the vertical ones, then automatically you have 3 pieces. If I have only 1 asymptote, then I'll have only 2 pieces.
Okay, thank you, sir.
Okay.
Then, sir, when you want to test, is it always that for the left side, you have to choose a value of maybe the horizontal asymptote, which is less than the given. Then for the side, you have to choose one which is greater.
You choose the value of the value of x that is less than the vertical asymptote.
Sir,
on the left. And on the right, that is
Sir.
bigger. Yes.
Is it that sometimes we can also have two horizontal asymptotes?
We can never.
Is it possible?
It's never.
Or it's only vertical?
Only vertical.
All right.
It's
Thank you.
never possible. So if you find
Mm.
yourself having two horizontal asymptotes, just know that things are not on the side that day. Bad. Okay, let's do another example. F of x is equal to, now I want something that's not sitting on. Okay, let's do this one. X squared minus 5x plus 4 over x squared plus 2x minus 15. How do we sketch this one? We go straight to the properties needed. Vertical asymptote is our first thing to find. X squared plus 2x minus 15 is equal to 0. Well, if I'm doing 11, 20, then I can use the general formula. Because in the exam, there will be calculators. But if I'm doing 1100, then it's just to look for factors. Like the factors are there. X squared minus 3x plus 5x minus 15. We get 0. So we have x minus 3. We have 5, x minus 3 is 0. So we get x is equal to 3 and x is equal to negative 5. These are the vertical asymptotes. Right. Therefore, the vertical asymptotes are x is equal to 3 and x is equal to negative 5. Then we find the horizontal asymptotes. Horizontal asymptotes, now we can guess. Since you said you can just observe. So let's observe so that those observing can also be at peace. So when we observe, we see that the powers of x are equal, the highest degrees are equal. So we divide the coefficients and get 1. Then we go to the y-intercept. The y-intercept, f of 0, that is 4 over negative 15. And then x-intercept, so the x-intercept, hello.
Let's take it back. How did you find the horizontal asymptote?
All right. So here we use the shortcut where you just observe. Maybe I should remind you for those who like the shortcuts when things are hard. Like if you have the function f of x is equal to ax power n plus other things over bx power m plus other things, where m and n are the highest degrees. We have two cases. Case 1 is if n is equal to m, the horizontal asymptote is equal to a over b. And case 2, if n is less than m, the horizontal asymptote is equal to 0. Case 3, if n is greater than m, this is not for first years. So all the 3 cases we talk about them. Case 1, that is what we are having here. X squared, so the highest degree up is square, down square. So we have 1 over 1. The coefficients. So if it was in this case is using case 2, where the degree of the numerator is less than of the denominator. So that's why it's 0. That's what we are calling observation method. The x-intercept, you equate x squared minus 5x plus 4 is equal to 0. So you do something like x squared minus x minus 4x plus 4 is 0. So you have x minus 1 minus 4, x minus 1 is 0. So you get x is equal to 1 or x is equal to 4. These are the x-intercepts. Now they are there. Okay. Then we want to sketch like this. But before you sketch, take note that these guys, if there is x in the numerator, and there was not a asymptote, I don't just know what happened. Don't remember what happened there. I need to comment as well. So if there is x in the numerator like this one, you equate the whole function. X squared minus 5x plus 4 over x squared plus 2x minus 15 to the horizontal asymptote. If the horizontal asymptote is not equal to 0, you equate, but you do equate as well, even if it is equal to 0. So when you equate, you get, in this case, we'll have x squared minus 5x plus 4 is equal to x squared plus 2x minus 15. So these will cancel, and then we'll have minus 7x is equal to minus, minus 19. Divide by next 7, divide by next 7. So get x is equal to 19 over 7. You know, this means that this graph will have an abnormal behavior where we have an asymptote that is being crossed at this particular value of x. So the vertical asymptotes, we have -5. We also have +3. So we have 3, we have -5. The horizontal asymptote is 1. We place it here. That is 1. Then now we get 3. Substitute in the function. So we have f of 3. F of 3 is going to be 9 minus 15 plus 4 over, not f of 3, a number bigger, bigger than 3. So let's put 10. I think 10. Because 10 is easy to use in calculations. So we have 100 minus 50 plus 4 over 100 plus 20 minus 15. This is equal to 100 minus 50, I get 50 plus 4, we have 54 over 120 minus 15, we have 105. So this number is less than 1. So it means that the curve is crossing on the right. So one of the x-intercepts that we have, the curve is crossing here. In fact, if we used 4, would have seen that would have gotten 0 since it's the intercept. So didn't just think about that one. So one of these two intercepts has been used. So x is equal to 4. We have used it. We're remaining with x is equal to 1. But we know when to use it when x is 19 over 7. 19 over 7. This number is 2 point something. So it's somewhere here. 19 over 7. Actually there, the graph would touch this guy. Beautiful. So then what's the y-intercept? The y-intercept is negative 4 over 3. So it means that we have negative 4 over 15. So this curve will be something like this. To touch here and go down like that. Because it's crossing the horizontal asymptote. Very strange behavior, which is acceptable. Then we pick a number less than negative 5, say negative 10. So we have 100 plus 50 plus 4 over 100 minus 20 minus 15. So here we get 154 over 80, 70, 65 over 65. This number is bigger than 1. So the curve is going to be up here. Yeah, like this. Okay, I can now attend questions. There's one here. Is it okay to use limits when finding the horizontal asymptotes here too? Very much okay. For as long as you get them well, you use them. So you use the limit to find the horizontal asymptote. It's very much acceptable. And that is the right way of doing things. The other observation method is kind of some guesswork. Mono.
Sir, I didn't really get the explanation you gave on how we found the horizontal asymptote.
So the horizontal asymptote, so I gave 2 explanations. One is where I use the limit. That one must have been well understood. The second one is where we just observe, looking at the powers of x in the numerator and in the denominator. There we only have 2 cases. The first case being when those powers are equal, like in this example. If the powers are equal, you go for the coefficients and divide them, the upper one over the lower one. If the power of the denominator is bigger than that of the numerator, then the horizontal is going to be 0. So here when we observed that x power 2 is the highest degree up, x power 2 is the highest degree down. So that's how we find ourselves relaxing with that thing there. Nyembe.
Sir, I'm still asking, sorry.
Okay.
So when we're finding these, these my drawings we're making through Manani cannot. We just get any number that is bigger than the asymptotes that we've plotted on the graph.
Yes.
Okay.
Let's move to Nyembe.
So why did you use 10?
It's bigger than 4.
Why is that?
Can you like explain like the whole function to one, and why, what does 19/7 has to do with the asymptote?
So that one, the 19/7 really has nothing to do with the graph. The only thing it's telling us is that it is giving us the value of x at which this middle graph here is going to cut what is called the asymptote. So what normally happens is that if there's a variable on top here, you equate this to, you equate that one to the, you get the whole function to the asymptote. Now, unfortunately, this meeting will be cutting soon, and that's where we'll end today. So, wish I could talk about this more, but I think this is a bit enough. So you equate the whole thing to 1 and solve for x so that you can know where to cut the horizontal asymptote, if there is. This 10 and -10, we're just picking numbers that are bigger than 4 and less than -5. Just like we are picking 5, any number you could pick here. Good night.
So for the x-intercepts, we had 1 and 4, but where have you